want to start off by mentioning Blue Planet is very appreciative of being part of this meeting, and we really thank CLF for thinking about having not only our technology but Will's and Marina's just being showcased in a conversation like this, because it's very important, especially with these upcoming technologies. But I'm just going to go straight into it. My name is Mohamad. As mentioned, I'm a carbon engineer here. I've been here for about 5 years, and I'm really excited to share this technology. I think it's mineralization in itself is really going to save the planet. And Blue Planet mineralizes CO2. And so what we try to do here is store gigatons of CO2 permanently into the built environment. As you guys may know, built environment is just a fancy word of saying our buildings. I won't go into this too much, but just really quick, you guys know the concrete impact, the global impact of concretes is 8% of global CO2 emissions. And if concrete itself was a country, it would be the third leading country in terms of CO2 emissions. That in itself is significant, and that's why we've targeted concrete to really try decarbonizing it and really making the built environment as the largest carbon sink in the world. So here's my favorite slide. I'm going to go straight into the products. I'm going to start with the two on the right, our upcycled aggregate. In the next slide, I'll really show our process, but one of our input materials is demolished and returned concrete, currently at our plant here in Pittsburgh, California. So with that demolished and returned concrete, we put it through kind of what we call like an acid wash. It strips away all that calcium oxide dust that really makes recycled concrete aggregate an issue to develop with. And so once we process that demolished and returned concrete, we're left with this liquid. That liquid is an alkaline solution. And for you to sequester CO2, which is an acid gas, you need a basic or alkaline solution like we've developed after we acid wash this upcycled aggregate. But the upcycled aggregate in itself is significant because it's recycled material. In comparison to RCA, you can put more of this upcycled material. RCA is just recycled concrete aggregate. Putting more of that material, you can replace more virgin aggregate with this upcycled aggregate in comparison to the recycled concrete aggregate. Both of these products meet ASTM C33, which is a standard for aggregate. And both of these really promote minimal environmental degradation. So so here in California, we have our material shipped from Canada and from Mexico. So rather than having to ship that material over many miles of ocean just to get to our material, we're providing this to local projects. And it's coming from the demolition of local projects as well. But going back to that liquid that we get after processing the demolished and returned concrete, that's what you need to sequester the CO2. And once we sequester the CO2, we make our calcium carbonate product. That's the two on the left. What's nice about manufacturing a product like this is that we can manufacture it to be round, as we showed in this picture here. We're manufacturing it now to make it look more like rocks, have different shapings to really promote tight packing, have a sand like we're showing here. It can be rough, smooth, oblong, depending on the concrete application. But what's nice about the calcium carbonate, it's all the CO2 that's sequestered into it. So by mass, calcium carbonate is 44% CO2. And an advantage of the calcium carbonate sand is that, or just calcium carbonate that we're producing in general, has a high reflectance. So when you replace enough of the concrete, the sand in the concrete with our calcium carbonate sand, you have a chance to increase the reflectivity of the surface of the concrete. So not only are we focused on the CO2, but this also impacts the albedo of the concrete and really fighting the heat island effect. And so here's our process a little more. I'm going to start off, let me see if I can get my pointer up. I'm going to start off with here, this reformation module. This reformation module is kind of what I was mentioning earlier, which is the acid wash. So we're getting this ammonium chloride solution, which is an acid. We're getting it in contact with geomass, and we term our upcycled, our demolished and returned concrete or other industrial waste as geomass. So once it comes in, we get it in contact with one another. You're left off with this upcycled material and wastewater. And then that solution is now an alkaline solution, which then goes into the CO2 absorption column. What comes out of there is calcium carbonate and a liquid. That liquid, once it's separated, is ammonium chloride, which goes straight back into the reformation module. So we have a circular process there, really minimizing the amount of chemical loss that we have in our process. And that slurry is further processed to make the rock that I showed in the slide before. What's nice about our process, I'll get into a little more, is we're taking CO2 directly from flue gas. And the material that comes out, this upcycled material, can also be mixed with the calcium carbonate. That's not what I showed in the slide before, but you can marry the two products to spread that CO2 out to a larger amount of products if need be. And this image right here is just a simplified version, but really just shows the circular process here. Here are other geomasses that we've recognized can do what our demolish and return concrete can do, but even better because there's more alkalinity that we can extract. So as I mentioned, you got the return and demolish concrete, you have cement kiln dust from a cement plant, steel slag that comes from a steel plant, fly ash that comes from a coal plant, bauxite residue that comes from alumina refineries, and then you have these raw quarry tailings, and all these really generate the alkalinity that we need to sequester the CO2. And we have other second generation geomasses that we're really looking forward into in the future, because as these, I guess, this resource becomes dwindled, we can start focusing on our second generation geomasses. This is just a quick, I'm just going to go through this real quick, but Carbon Star is a technical specification, and is becoming a standard that's developed by the Canadian Standard Association and supported by the Canadian government. And pretty much what it is, it's similar to an LCA and EPD, but it only focuses on the CO2 line item in the category. And so in this scenario, you have a very, very carbon intensive cement. William showed that the global cement efficiency is around 0.8, and that's what we're normally used to seeing. But in a scenario where you have a very carbon intensive cement here, you can replace both the coarse and fine aggregate with Blue Planet material. And to get the Carbon Star rating, you're taking the sum of both the carbon emitted and carbon sequestered section. And as you can see with Blue Planet material, you're capable of reaching a Carbon Star rating or a CO2 value of negative 500 pounds of CO2 per cubic yard of concrete, really making this concrete mix carbon negative. And this can go even more carbon negative if you include the brimstone cements, the SCMs, any other techniques that make this number go even lower in carbon negativity. So that's what's really exciting about this process. Here is Blue Planet's road to scale. So we've been in a lab phase for about 10 years. We still have our lab up and running, doing all these innovative techniques, but we currently are at a demonstration phase here at Pittsburgh, California, where we're sequestering CO2 at a much larger quantity, really making that calcium carbonate for us to test internally. And soon we'll be at a level 1, level 2 phase where we're producing enough material so that we can have third-party testers and really expanding the amount of CO2 we can really sequester. So what's exciting is we're really focused on this level 1 phase and how can we move up to a level 2 phase. This is kind of what we're looking at for our mineralization hubs. We're recognizing that when we go to a location, how do we put our plant in a place where we can maximize the amount of CO2 we produce and provide the maximum amount of calcium carbonate to the built environment. And so Blue Planet is here in the middle. What we're recognizing is we can take CO2 from any emitter. We've recognized that, currently our plant is, I'll just go back real quick. We're tied into what we call, across the street is a natural gas combined cycle plant owned by Calpine. So we take their CO2 directly from their flue stack. It comes to our property where we are directly mineralizing it to calcium carbonate. So this picture right here, this where I'm circling, that's where the tie-in to the flue stack is. That CO2 is coming across the road to our property. And that kind of ties into what we plan to do with any other CO2 emitter. We're going to take the geomass and flue gas from anyone we can really take it, but we've recognized that the CO2 and the geomass is the important input for us to recognize where we want to place the plant. And I'll just touch on it really quick, is we can also tie into a hydrogen plant. And because they produce, or methane is one of their inputs and hydrogen and CO2 is one of their outputs, we recognize we can take the CO2 from a hydrogen plant and really decarbonize hydrogen as well. And all that material would go into the built environment, into carbon negative materials and buildings, so that CO2 can again be the largest carbon sink. I mean, buildings and concrete can be the largest carbon sink for CO2. We've done what we've called a plant sprint. So we're going to different regions around the country and around the world in the near future to see where do we put these plants in other areas. And so we just came back from Seattle. We've done 3 trips of due diligence to recognize how do we find the site that we want, the CO2 emitter that we want to tie into, can we understand the geomass in that area, who would take the material and put it into the buildings, and understanding the government incentives to go in that region. And so, currently we focused on Seattle, but we were looking at Houston, Montreal, all these other locations to really put more plants and urgently sequester more CO2 in the country. And this goes away from our partners. We have partners like Mitsubishi, Chevron, and what they would do is something similar, but on their own plants. So we've recognized that we're not going to only wait for our partners to put more plants around the world, we're going to do it ourselves in these regions. We are what we term CO2 agnostic, and so we can tie in our technology to any flue gas source. So we recognize that currently we're at a power station, but we can be at a petrochemical or refinery facility, steel facility, cement plant, and hopefully in the future we can work with some direct air capture to sequester CO2 directly from the air. But again, the CO2 is not the issue for us. We can tie in, I mean, we can take CO2 at any concentrations. We've gone as low as 5% CO2 up to purified CO2. And we've recognized that as long as there's CO2 emissions, we can tie into there if these other categories that we've mentioned in this plant sprint are met. Really quickly, anywhere you think concrete can be poured, our aggregates can be put into that, with the thought that we can meet the ASTM standards for each one of these applications. So building ASTM standards are different than bridge ASTM standards. It's different than airways and so on and so forth. As long as we meet these specifications, we can pour our aggregates in these concretes. And hopefully in the future, we can meet all these applications. Just really quickly, I just wanted to share some concrete data. We've recognized that we can make our calcium carbonate concrete up to 6,000 PSI strengths. And these are with very early aggregates that we produced in the lab. And we've recognized the stuff that we're producing in the plant is reaching similar results. So it's very exciting to see that we're reaching the standard that we need to. As well as our UCA product, the material that's coming out is also reaching 6,000 PSI, and some of the other tests that really are focused on for developing building. But the material that's coming out, it's exciting because it serves the need of circularity and CO2, and they're passing the test that a lot of the developers here in the Bay Area are really keen on passing, which is compressive strength, shrinkage, and other stuff. Finally, some of the benefits that I've mentioned already, but some that I haven't. The product is carbon negative. And so in a scenario where we're taking the CO2 and accounting it with the calcium carbonate aggregate, it can make a concrete mix carbon negative and even a building carbon neutral if there's enough concrete to outweigh the steel and the other components of the building. As I mentioned, the reflectivity of our aggregate is 0.94. So that really can make an impact on the surface of concrete and really make it a lighter concrete in terms of color. And it's not like it's white concrete, it's still gray, but each 10% increase in solar reflectance has a huge impact, and us humans can't necessarily see the difference in color. And so that's why it's exciting. There's a lot of lead contribution points with just our products alone. Again, we directly capture CO2 from an emitter. The CO2 is permanently sequestered into the aggregate because it's through mineralization, and that's above ground. Our process is geomimetic, and so it also promotes the circular economy. So again, we're taking the waste streams of a metropolitan area and providing that upcycled, valorized product back to these metropolitan areas. There's a shortage to the sand. There's a solution to the sand shortage. That's in the construction world, there's a huge sand shortage. You can't just use the sand in like deserts. You're really dredging the ocean for the certain sand. So we're providing sand to the construction world. And then finally, we are what we term urban quarries. So rather than, again, having these materials coming from actual quarries, rock quarries, we're having our material provided from waste streams to the same people who provided us those waste streams. And I believe that's it. And again, I thank you for having us. If you guys have any questions, I'll be happy to answer.